Hello, friends. String theory is a highly complex and fascinating area of physics that aims to explain the fundamental nature of the universe. It is often referred to as the theory of everything because it attempts to reconcile two major branches of physics: general relativity, which describes the gravitational force and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of particles on the smallest scales. String theory proposes that the most basic building blocks of reality are not point-like particles, but rather tiny, vibrating strings. Each type of particle corresponds to a different vibrational mode of these strings. To start understanding string theory, imagine replacing the idea of particles as tiny dots with tiny loops or segments of string. These strings can vibrate at different frequencies, much like the strings on a musical instrument. Depending on how these strings vibrate, they can appear as different particles, such as electrons, quarks, or even photons. This is a radical departure from the traditional view, where particles are seen as distinct entities. Instead, in string theory, particles are simply different manifestations of the same underlying structure. One of the most remarkable aspects of string theory is its ability to incorporate gravity into the framework of quantum mechanics. Traditionally, these two areas of physics have been difficult to unify. General relativity, which describes gravity, works well for large objects like stars and planets. Quantum mechanics, on the other hand, describes the behavior of tiny particles like electrons and photons. When trying to apply both theories to very small scales, such as those present in black holes or the beginning of the universe, inconsistencies arise. String theory offers a potential solution by suggesting that all forces and particles can be described by the vibrations of strings. String theory also introduces the concept of extra dimensions. In our everyday experience, we are familiar with 3 dimensions of space and 1 of time. However, string theory suggests that there could be additional spatial dimensions that are curled up so tightly that we cannot perceive them. These extra dimensions are necessary for the mathematics of string theory to be consistent. While this idea might seem strange, it helps to explain some of the observed properties of particles and forces. The development of string theory has gone through several stages, each introducing new concepts and refinements. The earliest version, known as bosonic string theory, was developed in the late 1960s and early 1970s. This version only included bosons, which are particles that carry forces. However, it had significant shortcomings, such as predicting a particle with imaginary mass and not including fermions, which are the particles that make up matter. Later developments led to superstring theory, which incorporates supersymmetry. Supersymmetry is a theoretical symmetry that relates bosons and fermions. It suggests that for every particle we know, there is a corresponding superpartner particle. Superstring theory resolves many of the issues of bosonic string theory and is currently the most studied version of string theory. Another significant milestone in the development of string theory was the discovery of 5 different consistent string theories. Initially, this was seen as a problem because a theory of everything should ideally be unique. However, in the mid-1990s, a breakthrough known as the second superstring revolution, or M-theory, emerged. M-theory suggested that these 5 string theories are actually different aspects of a single underlying theory. This unifying framework also introduced the concept of membranes or branes, which are higher dimensional objects on which strings can end. A crucial component of string theory is the mathematical framework it employs. The equations governing string theory are highly complex and often require advanced techniques from geometry and topology. These mathematical tools help to describe how strings move and interact, as well as how extra dimensions are shaped. Understanding these equations is essential for making predictions and testing the theory. Despite its elegance and potential, string theory faces significant challenges. One major issue is that it is very difficult to test experimentally. The scales at which string theory operates are incredibly small, much smaller than what we can currently probe with our most powerful particle accelerators. This makes it challenging to find direct evidence for the existence of strings or extra dimensions. Another challenge is that string theory has a vast number of possible solutions. These solutions, or vacua, correspond to different possible ways the extra dimensions can be configured. This multitude of possibilities makes it hard to pinpoint which solution describes our universe. To gain broader acceptance within the scientific community, string theory must make verifiable predictions that can be tested. Some physicists hope that indirect evidence might come from cosmology or observations of black holes, where the effects of string theory might become apparent. Others are exploring connections between string theory and other areas of physics, such as condensed matter physics or quantum information theory, to find new ways of testing its predictions. String theory also has implications for our understanding of space and time. In classical physics, space and time are continuous and form a smooth backdrop against which events occur. However, string theory suggests that at the smallest scales, space and time might be discrete or have a more complex structure. This could lead to a fundamentally different picture of the fabric of reality, where space and time are emergent properties rather than fundamental aspects of nature. Another intriguing aspect of string theory is its connection to black holes. Black holes are regions of space where gravity is so strong that not even light can escape. According to general relativity, black holes are described by simple metrics, but their quantum properties are not well understood. String theory provides a framework for describing the quantum behavior of black holes, offering insights into phenomena like black hole entropy and the information paradox. These connections could help to resolve long-standing puzzles in theoretical physics. String theory also has profound implications for our understanding of the universe's origin and its ultimate fate. The theory suggests that the Big Bang might have been a transition from a previous state, possibly involving higher dimensional objects like brains colliding. This idea is explored in various cosmological models inspired by string theory, such as the ekpyrotic and cyclic models. These models offer alternative explanations for the early universe's conditions and the mechanisms driving its expansion. The historical development of string theory is a fascinating journey that reflects the evolution of our understanding of the universe. The idea of strings as fundamental objects emerged in the late 1960s, when physicists were trying to understand the strong nuclear force. Initially, string theory was not widely accepted, as it seemed to lack relevance to real-world physics. However, in the 1980s, it gained traction when it was realized that string theory could potentially unify all fundamental forces and particles. The development of supersymmetry in the 1970s was a crucial step. Supersymmetry proposed that every particle has a superpartner, doubling the number of fundamental particles and providing the mathematical structure necessary for a consistent theory. This led to the formulation of superstring theory, which resolved many issues with earlier versions of string theory. The discovery that there are 5 consistent superstring theories initially seemed problematic, as it contradicted the idea of a unique theory of everything. However, the development of M-theory in the mid-1990s provided a unifying framework that incorporated all 5 theories, suggesting they were different aspects of a single underlying theory. String theory's influence extends beyond particle physics. It has provided insights into other areas of physics, such as condensed matter physics and quantum information theory. For example, concepts from string theory have been used to study the behavior of materials at very low temperatures and the properties of superconductors. In quantum information theory, ideas from string theory have contributed to our understanding of entanglement and the nature of quantum computation. The mathematics of string theory is both sophisticated and beautiful. It employs advanced techniques from geometry, topology, and algebra. One key concept is that of Calabi-Yau manifolds, which are complex, multidimensional shapes that describe how the extra dimensions in string theory are compactified. These shapes determine the physical properties of the strings, and by extension, the properties of the particles and forces in our universe. Understanding these mathematical structures is crucial for making predictions and testing the theory. String theory has faced significant challenges and criticisms. One major criticism is its lack of experimental evidence. The energy scales at which string theory operates are so high that they are beyond the reach of current particle accelerators. This has led some physicists to question whether string theory can ever be empirically tested. Another criticism is the vast number of possible solutions, which makes it difficult to make specific predictions. Despite these challenges, string theory remains a leading candidate for a theory of everything due to its mathematical consistency and its ability to incorporate gravity into the quantum framework. The cultural and philosophical implications of string theory are profound. It challenges our conventional understanding of space, time, and reality. The idea of extra dimensions and the notion that all particles and forces are manifestations of tiny, vibrating strings can be difficult to grasp, yet it offers a compelling vision of the underlying simplicity and unity of the universe. String theory has also captured the imagination of the public and has been popularized through books, documentaries, and lectures. It has inspired a sense of wonder about the nature of reality and our place in the cosmos. In terms of popular science, string theory has become a significant cultural phenomenon. Books like The Elegant Universe by Brian Greene and Hyperspace by Michio Kaku have brought the complex ideas of string theory to a wider audience. These works help to demystify the subject, making it accessible to non-experts and sparking interest in the fundamental questions of physics. Documentaries and TV shows have also played a role in popularizing string theory, often featuring interviews with leading physicists and visually representing the abstract concepts through computer graphics and animations. String theory's impact on science education has been notable. It has become a topic of interest in physics courses at universities around the world. By introducing students to the ideas of string theory, educators hope to inspire the next generation of physicists and mathematicians. The theory's interdisciplinary nature, combining elements of quantum mechanics, general relativity, and advanced mathematics, makes it an excellent tool for teaching complex scientific concepts. The technological implications of string theory are still largely speculative, but they hold promise for the future. If string theory can be developed into a full-fledged theory of quantum gravity, it might provide new insights into the nature of space and time that could lead to advances in technology. For instance, understanding the quantum structure of space-time could lead to new ways of manipulating energy and matter at the most fundamental levels, potentially paving the way for revolutionary technologies. String theory's role in cosmology is also significant. It offers potential explanations for the conditions of the early universe and the mechanisms driving its expansion. Some models inspired by string theory suggest that our universe is part of a larger multiverse, with different regions of space-time having different physical properties. This idea could explain why certain fundamental constants in our universe appear fine-tuned for the existence of life. The multiverse concept, while speculative, opens up new possibilities for understanding the nature of reality and our place within it. Another area where string theory could have an impact is in understanding dark matter and dark energy. These mysterious components make up the majority of the universe's mass and energy, yet they remain poorly understood. String theory could provide new insights into their nature and how they interact with ordinary matter. By offering a framework that includes extra dimensions and new types of particles, string theory might help to explain the properties and behavior of dark matter and dark energy. The intersection of string theory with other fields of science and mathematics has led to unexpected and fruitful collaborations. For example, techniques developed in string theory have been applied to problems in pure mathematics, leading to new discoveries and insights. The interaction between string theorists and mathematicians has enriched both fields, demonstrating the deep connections between fundamental physics and advanced mathematics. String theory is a comprehensive and ambitious framework that seeks to explain the fundamental nature of reality by proposing that the basic constituents of the universe are tiny, vibrating strings. It provides a unified description of all forces and particles. The theory's requirement for extra dimensions and its complex mathematical structure make it a rich and challenging area of study. Despite the difficulties in testing its predictions, string theory continues to be a leading candidate for a theory of everything, offering deep insights into the nature of space, time, and the cosmos. Thank you for joining us on this journey about string theory. Please like, comment, and share the video. And please do not forget to subscribe for more videos.